Okay, this unit is magnetic forces and the field. Okay, unlike electric field, because in electric field there's a positive charge and the negative charge, and then if there's a electric field that creates going this way, like that. So if I release a little tiny positive test charge, then it's going to travel along that electric field. And then you've seen this picture before, magnet with a bunch of iron on it, and then north pole, south pole. So we are imagining electric field, I mean the magnetic field in that direction. You know what I'm saying? So we've seen this picture, and this thing goes out to infinity, right? So if you put two magnets together, north and the south, and then magnetic field that we are introducing. But what direction? What is our test, not charge, but test magnet, right? So imagine introducing a compass, little compass, you know what I'm saying? Like that, north, south. Then this thingy will be attracted to the south. This is a little north and little south. And then this will be attracted to the north pole, so it'll, right? And as we move this thing along, it's going to look like this. That makes sense to you? So that's a direction that we are imagining, which doesn't really exist, but we are kind of imagining there will be some field lines, flux lines going through like that, right? And then if you put two nodes together and they hate each other, they repel, so it's like, right, good. And then do you guys know that not all conductors are attracted to magnet, right? It's mostly iron, and there are a few other materials that's attracted to magnet, but most conductors do not really care if there's a magnetic field or not. So what happens if you float a little charge inside a magnetic field? And nothing happens. Okay. Charge does not generally, well, let me correct that. Stationary charge does not get really affected by the magnetic field. However, give that charge a velocity, the moving charge, now there's a force. And that force is given by this formula. And that's such a weird formula, right? So if it moves fast, let's just pick it apart. It's a cross product, and there's a reason why it's a cross product. Let's just think about that a little bit, okay? Here's a little diagram, positive charge, okay? If the direction of the velocity is upward, and the magnetic field is that way, then force is that direction. Really? It's perpendicular to both of them. That's why we use cross product. But if this positive charge moves parallel to the field, then nothing happens. It doesn't feel anything. Well, only when it goes across at some angle other than zero, the magnetic field, then it feels the force. It's weird. So what is proportional to is the amount of charge. And by the way, if it's negative charge, the direction of the force is exactly opposite. So we can think about this as just positive negativeness or just magnitude and figure out the direction. But negative charges will have the force exactly in opposite direction of the positive charges. Okay? Now, and so it's proportional to the charge, and it's also proportional to the velocity. If it's moving faster, then force is greater. And of course, it has to do with the amount of the magnitude of the field itself. So it depends on those three things. And of course, sine theta, cross products, magnitude is a sine of that angle in between. And that angle here is, say if it's moving that way, let me draw it. If it's moving that way, and that's the angle. Okay, so the angle between the field, where the velocity and the field and cross product, if it's not commutative, if you switch the two, then you get the opposite answer. So it's V cross B, not the other way around. So it's like right-hand rule. So cross product goes like this, right? The first vector, second vector, and it's got to be perpendicular to both, but not this way. It has to be upward. First vector, second vector, upward, right? So people use two of these right-hand rules. One way is that you extend your finger this way, and then it only bends to the. You have seen this in a math class, right? Your finger only bends that way, so that your direction of your thumb is the direction of the cross product. Or in physics, especially when you're doing this, we use this hand thingy a lot. So your thumb is your velocity, and notice that angle is not necessarily right. So this is kind of more useful, 90 degrees. And then field, magnetic field are your fingers, many, right? Represents many lines like this. And then direction of your palm is your force, kind of like in Star Wars when you force somebody, your palm force, you get it? So it's like force. Okay. Star Wars has contributed so much to physics, I'm telling you. And how did they come up with this, right? Experiment. Physics is an experimental science, so they measured it in many, many different ways, and then they came up with that. How do you measure such a thing? How do you measure a force that is acting on a tiny little particle such as proton, or you know what I'm saying? Yes.
Do they try to like use a lot of them? Like try to measure the whole field somehow?
Well, I'm going to explain. And it has to do with the mass spectrometer. This is how you enrich uranium, by the way. So same idea. But before we do that, I have to teach you the little notation, the convention, okay? Say there's an arrow. You know what I'm saying? If you look at it from this direction, what does it look like? If you look at it from this direction, it looks like, right? So when they put a bunch of these dots, because these things are perpendicular and it's difficult to put it in two-dimensional paper, that means your arrow is poking out of the page. You get it? Sometimes they put these circles around. That means coming out of the page, right? And then if they put a bunch of X's, that means your magnetic field is going into the page and you're looking at the back end of the arrow. So that's by convention, so that we can draw the direction of the velocity and forces, okay? So say there's a magnetic field coming out of the page like this. I'm going to draw the field in different colors so it's easier to see. So this is the field coming out of the page, and it's uniform field. Like that. And then you take positively charged, here's a little thingy called velocity selector. I'm going to talk about how they do such a thing. Accelerate the positively charged, whatever, proton or the little tiny element. And then you give initial velocity coming in that way, v. Right. Now let's figure out the direction with our right-hand rule. Which way is the force, right? Force is going in coming out of the page, right? Coming out of the page. And then you align your thumb, the field is coming out of the page. You align your thumb along your velocity, and then you see your force is that way, right? Do you see that?
I'm see the hand in front of us.
Okay. Align your thumb towards the velocity, and then align your fingers with the magnetic field, which is coming out of the page. And then you see the direction of your thumb is the force. So it's that way, right? Okay, so then my question is, does it fly off like that? Well, let's see. At the moment, let's say velocity has turned that direction, right? Now let's do this again. Your fingers are still coming out of the page, right? But now your thumb is tilted in about that 30-degree angle. So you see your force has to be in that direction now. So it's kind of like doing 360 with a basketball. Your palm is on the side of your ball, and then you're constantly pushing it around. So the path of this particle will be semicircular like that. Right? So at any given point, if this is a velocity, this is a force. And then if this is a velocity right there, then force is this way. And if velocity is that way, and then force is that way. Oh, in other words, this force due to magnetic field is centripetal force. So we're going to tie that together with the mechanics. So far with me? Okay. So earlier, I told you this force due to magnetic field is Q, and then velocity cross product with the magnetic field. Right? So let's look at the magnitude of this thing. It's Q, V, B, and a sine theta. Yes? I have no idea. But then in my college days, my professors use H a lot, and there's a subtle little difference between B and an H, but I forgot that difference, so hey, I don't know. Okay, now then, what is the angle between the velocity and the field and the velocity? Is always perpendicular, isn't it? Because it's coming out of page. So this thingy is equal to 1 now. So it's just Q times V, okay? But then, do we remember what centripetal force was? Was it mv squared over r? R being the radius of whatever this. Good? Okay. Well, we want to equate the two then, don't we? Yeah, let's equate these two forces because this force upon this real force due to magnetic field is acting as a centripetal force. Good? Okay, so we have Q, B, B is equal to mv squared over r. And this is the key thing that you have to do over and over in AP. Okay, instead of memorizing whatever the result we get, we should always set it up and do it this way. Okay, and then what should we solve for? I mean, we can solve for anything, but shall we solve for this r, or just fun of it? Because I want to teach you how to enrich uranium. Okay, so r over here, so we divide one of the v divides, and so we have m v over r b, like that. Q, I forgot Q. There's a Q. QV, huh? Oh my God, R is here. Nice catch, like that. Let's just stare at this for a sec. Is it, m is constant, right? Velocity, once it comes out of this thing, is constant. Q, charge of the particle doesn't change once you charge it and release it. And B is constant, which means this R is constant. So we, as we expected, we just get this perfectly circular motion. Okay, that justifies something. Now, enriching, before we get to this, I'm going to shove this thing down a little bit. Enriching uranium. U-235 versus U-238. Okay, this is common one. Most common uranium in the world, most of it, which is useless. It does nothing. Half-life of this is like billions of years. I mean, it's very stable. This is a bond-making material. Just missing 3 neutrons, and neutrons are the ones that holds this nucleus of this somewhat unstable element together. So by missing those 3, that makes this nucleus pretty unstable, and it has a rather short half-life. So it tends to go off, right? But it's not like here's a pile of U-235 and here's a pile of 238 and we just want to mine 238. No, they're all mixed together, atom by atom. So how do you separate these atoms together? You feed it into this mass spectrometer, old technology. And this radius depends on the mass. And you think heavier material will have bigger radius, and then lighter material will have smaller radius. That makes sense to you? So these 2 atoms, if you charge it positively and shoot it through this thing, have a 2 different locations where it lands. So you just put a little collector here where the 235 path is, and 238 path will be bigger than this, and you just throw that away. You don't care about that one. And they literally collected these atom by atom. It takes a long time to enrich uranium. These days they use the technology called centrifuge, which is not exactly the same as this, but you can see how the magnetic field is used in enriching uranium. Okay, now say if it's moving in exactly perpendicular that way, then it's going to just go in a circle forever. However, what happens if it's a little bit upward or a little bit downward? Let's say a little bit upward, aligned with this field. Then what you can see is this helical path, circular motion plus whatever the little velocity you have in that direction. So it's like that's generally how a charged particle moves along in the magnetic field. Okay, so far so good? Okay. Here's an example. If you shoot a beam of electron, then it'll go in a circle like that, and they actually put a picture of that thing. Okay? Now, then, A, you have to find the magnitude of the magnetic field this time. Okay? And B, what is the angular velocity of this electron? Okay? So let's figure those out. So let's do A first. First things first, what's the direction of this magnetic field? Now, remember, this is electrons, so instead of right hand, you use your left hand, because that's the opposite direction if you put your palms together, right? Or figure out the right hand and reverse. Why do that? So left hand. So we don't know, but we align this thing upward, right? And then either it's this way or is it, so it's curving in this direction, right? So your force is inward. So your palm has to be inward. You know what I'm saying? So do you see that this magnetic field in this case has to be going into the page? Do you see it? Do you agree with that? Go into the page, left hand, and then goes around. Get it? Think about basketball 360. You know what I'm saying? Okay, so we know the direction now, at least. Usually when you are figuring out cross product, you want to figure the direction out first, and after that it's just sine theta in between, okay? Okay, but before we do that, we need velocity of this thing first, right? Because velocity is not given, but we're given this. Okay, so you see kinetic energy at the final has to be same as the potential energy initial. Okay, so kinetic energy, of course, is 1/2 mv squared. What's the potential energy in electric field? Because you're using this much electric field before it enters it to accelerate this thing, and now it's inside the magnetic field, right? So do you remember it has to be charge times Potential? Potential energy meaning potential times amount. See, MGH idea, MGH, potential energy, is really M times GH. You know what I'm saying? And GH is the potential part, and this is your, how heavy you are. So same idea, the charge, I put absolute value because this is negative charge and it gets really confusing, right? And then delta V. Okay, so your V has to be square root of 2 and then Q delta V over M. You get it? So with these numbers, you can plug in the numbers and calculate this. So far so good? Now then, F, once again, due to magnetic field, is now Q, V. Q is given, and V, from this V, you plug it in, and then we use V, or cross product, but the angle between the two is the 1. I mean, angle between the two is 90 degrees, so sine theta is 1, as we did before. So far, so good? Okay, now, of course, centripetal acceleration is still mv squared over r. And they can measure the radius of this thing. Good. Now we equate the two as always. This time we are solving for b. So b happens to be one of the v cancels mv over q times r. You see how we can use this relationship. You start here and then you ask, equate them, and you ask yourself, what is it that I want? And then you solve for that. That's how things work in physics all the time. Good? Now part B. Angular speed of this thing, well, you guys remember this. Linear velocity over radius. You get it? And that's it. We don't really have to do much, because radius is given in this problem, and velocity, we figured it out here. Okay, so now then how do they, because here in spectrometer, if you have different velocity, then you're going to have different paths, right? Stronger velocity means bigger radius. So you cannot have that. You have to select this particle with exact same velocity only. How are you going to achieve such a thing? And here's the idea. This is known as velocity selector. Okay? This time, see here, they put two capacitors, so two plates, positive, negative. Then electric charge will move from the left to the right, in this case. Good? And then you send from the source some charged particle, let's say positively charged particle. Then that charged particle will want to move along this path because it gets pushed by that field. So far, so good? Now we're going to balance that by magnetic field going into the page. So let's try this again. If you put your fingers into the page and align your thumb with your right hand, then you see the magnetic field is going to go in a circular motion like that. And we find the force equilibrium. You get it? It's not that everything works, because depending on the amount of charge and the mass, right? So certain things will depending on, let's say, different velocity, certain things will go this way and certain things will go this way, and then they just never make it. But whatever comes out here is exactly the balance between the two. And then let's see if we can get a uniform velocity out of that. Good? So this thingy, I'll put cross product QV cross V. Good? And at the moment, the magnitude is just QVB because the angle is 90 degrees. Good? Now, what is the force of the electric field? It has to do with Q, and then what else does it depend on? It's this. So that magnitude is equal to just Q and then magnitude of E. By the way, E and B are both known. We, the scientists, control our experiment apparatus. Now we equate the two. So we have QVB is equal to QE. And as you can see, Q's cancel out. So your velocity is E over B. So only the particles with this certain velocity will make it through. Anything faster or slower will crash to the side. And that's what you put into mass spectrometer like that. Okay. I guess I don't have to explain this again because I pretty much did earlier, right? Up here. So this is mass spectrometer. I just got overly excited and just talked about it. So we'll skip this. Well then, there's a cyclotron. If you go to Berkeley campus, see, Professor Lawrence is the first Nobel Prize winner from Berkeley. And his Nobel Prize is by inventing this cyclotron, particle accelerator. And this thing, weights coming out is like almost close to the speed of light, that kind of acceleration. And then he did a lot of work in this, okay? And they built, the original one is about, diameter of this thing is about the size of this room right now. But then they built a cyclotron 2, and they named it Bevatron. Sounds like Transformer thing, right? Oh, that's where the writers in the movie got the name. Bevatron is approximately size of that P building next to us. I mean, it's a huge cylindrical building, and elementary school kids come on a field trip at there, and it's like, it's a big site, okay? So anyway, it's not a small thing. The way it works is they have giant electromagnet, and I will explain later how to create such a thing. But you guys kind of done it before, like nail coil around the... Oh, okay, I'm going to explain later how to create electromagnets. So up, one on top, this is like inside view. And this is huge amount of magnetic field, right? And then you start the particle in an acceleration, let's say in that direction. Okay? Then can you line up your fingers upward and velocity so that direction of this will be in that circular motion? So far, so good. Okay. Now, but when it's passing these two, they charge this huge part with the, let's say, positive charge, and they charge this side with a negative charge. Which means in the gap, there will be an electric field going that way. You know what I'm saying? And that will accelerate this charge a little faster. So as it goes through this, now it's going a little faster, which means this radius just grew. Right? Because faster particle means bigger radius. Now, by the time it enters it, it's going to slow it down because there's a positive, this is a positively charged particle, so, right? But there's an alternating current here. You switch the positive and negative as soon as it passes through. So by the time it goes around, this thingy gets charged positive now, and that thingy gets charged negative. So we'll create the electric field, and it accelerates the particle even more. And it just goes to that side, and that radius grew, and the other side it'll grow again, and then grow again, and by the time it comes out, if the angular velocity of this is constant, that's the only thing, or if the period of this thing, time it takes to go around, is constant, and I'm going to have to prove it to you why that they are constant, but if that's the case, then as this thing is, if this thing is big enough, then we take exact same time to go around it, so you see how this thing has to be pretty fast. And you can come like near speed of light. And then you hit that with another nucleus of an atom and break the atom apart, and a whole lot of weird particles fly out, and you study that in something called bubble chamber. I remember that experiment. Oh, it was complicated, to say the least. Okay, so this is the physics behind the cyclotron. Okay, so let's start. So remember this is equal to V over R, correct? Okay. Do we remember V from previous? V from the, let's do it over. It's healthy to keep doing this thing over and over, okay? So let's do it here. Your force of magnetic field is QVB, perpendicular, and then your force, centripetal force, is equal to mv squared over r. So you equate the two. I mean, this thing should be automatic, okay? Then v, here, one of them cancels, so we have q, b, q, r, r, capital R, and then b over m is what you get. You know what I'm saying? I have to change this to capital R because I'm using capital R over there, and whatever, right? And then you substitute it right there. Good? So what we get is this thing is equal to Q R B over M over, I'll just put R here. And then these R's cancel. So you get QB over M. What's so big sticking deal? Well, this is constant in R. Meaning, angular velocity does not change in terms of R, even if it goes in a bigger radius. Your period, therefore, you guys remember period and angular velocity, right? So period is constant. Huh. Which means this technology will work. Yes, question?
That means that they can alternate it. Knowing the period, they can alternate it.
Because they know the period, so that they set up this alternating current at exactly that period, and you flip it, the half of the period, right? So you set the period of this alternating current exactly the same as the period of this thingy, and then they can accelerate this. And only thing is just bigger magnetic field and then bigger cyclotron. Therefore, they want to see bigger magnetic field depends on the bigger coil up and down. So more the reason to make this thing huge. So that's the particle accelerator. Okay. Now let's figure out, well, what about if there's a wire? Wire is moving charge, isn't it? So that gets affected by the magnetic field. Okay, first we'll figure out the direction of the force, and then we'll figure out the magnitude of this thing. So we put the magnet, you know, this U-shaped magnet around the wire, then how does it bend the wire? Okay, if the current is zero, then of course, predictably, there's no charge movement inside the wire, so there's nothing. But let's say there's a real electrons flowing downward, but positive current moving upward, right? So we can do this again. Put your fingers into the page, and then you put your thumb up, then you see your force is this way. So your wire bends in that direction. And then if the current is downward, then you put your thumb down, and then you can only put, right? So that's the direction of the which way the wire is bent. Good? Now, then we need to figure out the amount, right? Because your force of the magnetic field is given by this. Right? Okay, so that's really not helpful, because what we are given is this, correct? But do you remember what this definition of current was? It's a derivative of charge. So amount of charge passes through some cross-section of your wire at certain time, given time. You know what I'm saying? But if this thing doesn't vary, and if it's constant, if I is constant, then we can say this is equal to delta Q over delta T, right? Or constant I, which tells you that amount of charge that passes through, because this thing is given in terms of charge, you get it? Is equal to your current times delta T, and that's nice. And we are going to substitute that in here, okay? So what we are going to have is I delta T, good, times V cross V, B. So far with me? So far with me? Okay. Then what is velocity times time? Mechanics. Certain velocity, then you have amount of time. Is that the displacement?
Yes.
Yeah, it would be the displacement, right? Delta x, that's, so we'll just say this is L, the length. L being whatever's inside, L is this much. Whatever's exposed inside the magnetic field, right? But still with the direction, so this direction is the direction of the current, cross product with this. You get it? Say yes. Okay. Then say this, that's if this wire is so straight and nice, right? What happens if it's not as nice? If we have bendy, curvy wire inside the magnetic field? I mean, let's assume that magnetic field is constant because you can control that. Then we just take a differential on both sides. So your dF due to magnetic field is, this I is constant current, and this just replace that with ds. And then we integrate it. So we get this kind of expression. You get it? How about that? Good. Now we're going to take an example and do this integration for real. Okay. So we have this kind of wire and current flow is to the right here and then go through this semicircular path. Is a constant current I. Okay. And then we have to calculate the force acting on wire, this part as well as that part. And then let's see. Okay. First, let's figure out the direction of this force, shall we? Okay, so let's do this part first. So put your fingers aligned with the field upward, and then thumb towards the direction of the current, which is direction of the charge to the right. Then force is coming out of page. So force here, you can see is coming out of page like that. I'll just throw it here. So far so good. Then what about this upper portion? Well, your fingers stay the same, but your thumb flips the direction to the other side. And this thing is not constant. This one at the bottom will be constant, but at the top it won't be constant, but nevertheless, it will be going into the page, wouldn't it? Okay, which means if this wire, this thingy is free to rotate, then it will actually flip over. And then line itself up perpendicular to this magnetic field, and it stops moving. You kind of get the idea of how the electric motors work now? Yeah, because if you have a current in a coil inside a magnetic field, then it will realign itself. And then remember that alternating current idea here? Then you alternate the current. Then this thing will stay in motion forever. Okay, that's the idea behind electric motors now, but we'll calculate this now. So F1, let's say is this one, and F2 is that one, okay? F1 is easier. F1 is your I, and then some path one is the down one, and then your ds cross b. Good. And here, the field and the direction, ds is tiny bit that way, right? They are perpendicular, so this cross product just gives you 1, doesn't it? So what we have here is just I, and then path 1, and then b times ds, and then k vector to make sure this is still a vector. Good. But then b itself is constant, so it can come out. Then we have path 1, and then just ds and k vector, eh? Wait, what is this integral? When you integrate something without anything, well, integrate 1, doesn't that give you that length of that path? And that path from here to here happens to be r is here, so 2r here. You know what I mean? So this thingy is then I b times 2r. How about that? Okay, and that's the amount of force in upward direction. Good, 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 good. Okay, F2. F2 you have to really think about it a little bit and integrate. So that is still I, and then C2. C2 is the upper semicircular path moving in counterclockwise direction. And then ds, cross that with B. Okay? And then that is I over C2 path, and then B sine theta, right? Cross product has a sine theta, but what's the direction? Now it's going into the page, right? So we'll say that is negative k. Good, 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 good. Now we have to think a little bit. What is ds? ds is a tiny little arc length right here, right? Do you remember the arc length formula? ds is equal to r d theta, right? Wait, theta? This theta? Yes, that theta. So what we have now is, take the negative sign out here, and I and b now is constant. Good. And then, only thing that varies due to this angle is sine theta. And then we can put d theta, and then k vector here. Right? And theta will vary from 0 to pi. How's that? Because our angle, 0 to pi, general angle. 0 degrees here, and pi, 0 radian, pi radian.
So I just want to make sure, where does R go in the bottom?
Did I drop R? Oh, you caught me again. You saved me again. R, of course, is here. I forgot. So far, so good? Okay, and after this, it's just calculus. And then, is this negative cosine theta? Wait, if we use plumbing professor, substitute this, give you 1 minus negative 1. So this quantity is 2. So we have negative 2 I, B, R, K vector. So it's telling you it's downward, negative sign, and I, B, R, right? Turns out it's exactly the same amount as this, isn't it? And that's kind of telling you something, by the way. You see this magnitude is exact same magnitude as that. Because of this sine theta, even if you're traveling in a greater arc, you remember line integral, right? Yeah, it's that kind of thing. Instead of a cosine theta and a dot product, it works exactly the same way. So far, so good. So remember, this thing wants to rotate and align itself, right? So we want to calculate the torque. If there is a loop of a wire with a carrying current I, and magnetic field is on a side like this, then how much torque, because it will rotate and flip, right? So how much torque will be exerted on this? And this is the how you build the electric motor by putting the axle right here. So hopefully it will rotate. Okay, let's just figure that out, shall we? So a couple of things we need to remember. The torque itself is R cross F. Okay? Okay, and then, of course, this force of the due to magnetic field is, in this case, I, L being the length inside, exposed inside the magnetic field, and then cross the B. Okay? Okay, let's figure out the direction of the forces, shall we? Okay, so let's say path 1. You put your fingers across, right? And then direction. What is the angle here? This is parallel 180 degrees, which means if you take a cross product, it's 0. It's this cross product right here, right? Okay, so your force F1 is equal to 0, is what we see here. Likewise here then, F3 will be 0 here as well. So far we know that those two. Okay, then let's look at F2. Okay, so you put your forces, put your fingers along with the magnetic field, and then your thumb downward. You know what I'm saying? Do you see that direction of the force is coming out of the page? Can you think like that? Right? Your thumb is pointing at you on your page. Your palm is pointing at you. See, whenever there's a ENM portion of the AP exam, there are so many hand thingy going on, and some students are twisting their arm around to align these things. This happens a lot, and if the proctor does not know, are you guys cheating together, some kind of hand signal? Right, so that it's up to the physics teacher to remind the proctor, this is not a cheating signal, this is cross product that they're trying to figure out. Well, the other side is easy because it's opposite direction, so that side, force must be going into the page then, eh? Should we do it? Put your right fingers to the right and thumb up, and then your palm points into the page. Yeah, which means it will create a rotation, right? So this is the little diagram. This side is up out of the page, and this side is down into the page. This is a cross-sectional view. Looking at it from the top. You know what I'm saying? Well, from bottom, from this point of view. You're looking at it from this direction. Okay, so now we can calculate the torque, the magnitude of the torque, because we already know the direction. Okay, and R cross F, so the radius here is half of, well, the dimension is this length is A and this length is B in this loop. So B over 2 times F2. Good. And the sine theta. Now, sine theta here is not always perpendicular. It's perpendicular at the moment, but as soon as this thing rotates, it's not so perpendicular. So we have to keep sine theta here, right? Okay, then we're going to have the other one, this F4, which is B over 2. Wait, that's exactly the same amount, isn't it? Right? Now, then we can combine the two, B over 2, B over 2. These two are like terms because F is IL cross B. Good? So we combine the two, so this is just B, and then F is going to be IL cross B, like that, huh? So far, so good. Now, what was L? The length in this case? It's A, correct? So we replace this L with A now. With me? So what we have here is I, let's say AB, lowercase, and capital B, magnetic field, and sine theta. Good? Wait, what's A times B in a rectangle? That's area of the rectangle, isn't it? So far so good? A being the area of the rectangle. This area. Because A times B, length times width, is the area. Okay, now, remember these things are vectors, right? So one of the more convenient way to express this is, I'm going to write it in red, the torque is a vector, by the way, is equal to I A cross B. What? Okay, we know what direction of B is, but we don't know what is the direction of the area. Well, we just use the right-hand rule again, right? And then it's coming out. Those of you in multivariable calculus, it's kind of like, remember Gauss's law? That area, ds, had a direction, so its direction is coming outward. How about that? Good? So, see, this is how you figure it out. You kind of figure out that it's in a loop, and then your direction of the plane is upward where your thumb is. Good? That way you can express this with a cross product. And it has to do with the area of the whole loop. Really, because this is perpendicular exactly or parallel, so this is a convenient loop. What happens if it's circular or any other weird shape? Then do you believe this will be exactly this? Well, here's an insight. Remember this problem? Yeah, this force of acting on this wire throughout the integration happens to be exactly the same as this. So it doesn't matter what shape of the wire that we have, it will still be exactly the same. So this actually works for any shape of wire. If there's a loop inside the magnetic field, then there will be a torque. It will rotate until it's looking like this and stop. But then if you switch the direction of the current, by then with some alternating current, then it will feel and then momentum will still carry it past that equilibrium, and then it will flip to the other direction, and you create this thing moving forever. Good? Okay, then. This thingy, right? People define this thingy. I'm going to call it mu. By definition, it's just IA. A meaning the area of the loop. And this thing, this mu, is known as the magnetic dipole moment. Magnetic dipole moment. Okay, it's just one of the things that shows up a lot, especially in electric motors. But this is just one loop. But once you're going to put this thing inside and to make an electric motor, why do you put one loop when you can have a lot of loops and make solenoid out of it? So this thingy, in case if it's a coil, then it'll be number of turns in that coil, number of loops in the wire times I cross A. Right? Okay. We'll just talk about this and then we'll call it a day. This is how railgun works. And this is such a, you know what I'm saying? So railgun, you put some kind of mass. In this case, it's just a rod, but whatever the thing that you projectile you want to put inside the railgun goes here. Okay? And you have very strong magnetic field either pointing upward or downward. And in this case, let's just put it downward. Okay? Then you charge one of this rail with a positive and one of this. Let's say this case, this is the positive side, and this is a negatively charged rail. And then this is a metal, this is a conductor. So there will be an electric current moving in that direction. Get the idea? So whenever there's a charged particle moving in the magnetic field, there will be a force. Okay, job number one, we'll figure out the direction of that force. So put your fingers downward and align the thumb. Do you see that force is this direction? Right hand.
Yeah.
Okay. So there will be a force, but then this is just free to slide, right? So this becomes a projectile and accelerate in that direction. And our job is to figure out, well, amount of acceleration or what is the final velocity after it leaves the rail of L meters. Okay? I'll just give you an idea and leave this as an exercise. So this thing is, in this case, your I, and then L. L is this misleading because I have L here. Okay, D. Our L is now D, right? Cross B. Good? So the magnitude of this force, because we know the direction now, is just I, D, B. And D, they can measure, this is the width of the rail gun. And then, you know, the magnetic, oh, that looks like a derivative. They use, this problem use D, so that's the distance D, width between the rails. And then B is the magnetic field that we can control. And then I is the current that we can control, depending on the potential difference between the two. Okay, and then once you have force, then it's easy. Then F is equal to ma now, right? And you know the mass of this thing, so A is equal to F over m, then you figure out your acceleration. Once you have acceleration and you have distance, then you can figure out the final velocity, eh? Remember this? V2 squared minus V1 squared is equal to 2A delta, in this case, delta x is L. And this is 0, so, right? So a bunch of substitutions later, you figure out your final velocity of your projectile. And they can fire this really, I mean, depending on the length of this gun and the field strength. But if this is sitting on the top of a destroyer, I mean, you can make this thing pretty large scale and very, very strong. And then you can fire this projectile really, really far. So that whenever US Navy built the USS Somalt, that was the idea. Instead of missile destroyer, yes, question? Oh, railgun is the piece of technology. Can you imagine this is a gigantic cannon and then it fires this thingy rod out that way? And this is just no explosive piece of metal, but kinetic energy alone will destroy a lot of things, right? So you can, instead of having a guided missile destroyer, which is complicated, and thing about missile is once you fire it, it tends to give away your location with all that flame and smoke and everything. This is and then missiles can be shot down. This thing is like about yay big. I mean, it's really small, but it moves so fast. Way into I'm not even like very fast, hypersonic speed. Then it can destroy a lot of things.
It's like a giant bullet.
Yeah, it's a really giant bullet. So that's, United States built a couple of destroyers based on this. It's got missiles too, but its main weapon is 2 railguns on top. Except they had to scrap that idea, and this destroyer is useless now. Reason being is, remember it has to glide on top of this thing? That creates a friction. And it's moving so fast that actually this thing catches a fire. Well, it's a metal, so it's like it's not gonna catch a fire, but it gets hot, and then after so many shots, this thing bends and melts, and you have to throw the gun away. So it turns out this is very expensive. And missiles end up being cheaper than this. So they scrapped that idea, and that is a very expensive conventional destroyer. Yeah, I know. That was a nice idea, though. Okay, let's call it a day today.